Thanks very much to Hervé and Moshe for inviting me as a senior member of the EC community. It's a great honor and pleasure to speak in front of many, many old friends and colleagues. As Moshe said, I want to talk today about fair algorithms for machine learning. I'm emphasizing the word algorithms here for reasons that I hope will become clear shortly. But let me first just set a little bit of context that I think many of you are familiar with, because these days you don't have to kind of go to NIPS or ICML to know about what's going on in machine learning. You can just pick up the New York Times or the Wall Street Journal or Forbes or any other mainstream publication. And so it really seems as if, just as the machine learning community was enjoying its 15 minutes of fame after 30 years of toiling in obscurity, we find that all of these reports, these kind of buzz-killing reports about essentially machine learning violating various social norms occurring, in particular things like unfairness or discrimination. And there's many, many reports, there are many, many scientific papers and less scientific studies of these kinds of things, and it occurs across a great range of kind of decision making. And while we may disagree about how important it is that each little ad that Google shows you is chosen fairly in some sense, at the other extreme, I think we can all agree that when machine learning and statistical modeling is used to make very consequential decisions about individual citizens' lives, like criminal sentencing or credit and lending or employment or college admissions, there's quite a bit at stake. And I'm not going to kind of go into all of these different kinds of reports, but they range from things like, statistical models systematically discriminating against racial groups in the appropriation of credit or in criminal sentencing decisions. There's been very recent work in the machine learning community, probably by some people in this room, on the fact that many of the large-scale language models that are used by Google and are now open sourced have systematic gender bias in them. There's things like discriminatory pricing on Amazon that might be correlated with various racial groups or gender groups or other unknown kind of axes of discrimination. And it's even gotten to the point that there's a general audience book that I actually recommend. If you're in the field, it may not tell you anything technically that you didn't know, but first of all, it has an incredibly clever title, Weapons of Math Destruction, and it also just lays out in a very sweeping way all of the different ways that unfairness and discrimination creep into statistical modeling and machine learning and related activities, and the consequences that it really has, not just on companies, but on specific people's individual lives. And so this is part of this broader trend that we're seeing, that as machine learning has become ubiquitous and deployed at scale, not just for things that it's been used for a long time, like people, quants on Wall Street trying to predict a directional movement of the markets, but really making decisions about specific citizens, it's starting to collide with various kinds of social norms. And so here's some sample social norms. I'm mainly going to talk about fairness today, but obviously there's great concern about whether machine learning models in their usage or in their release might be violating privacy of individual citizens in some ways. As these models are being used to make decisions about employment, credit, and the like, people are concerned about interpretability and transparency, and in the case of things like self-driving cars, issues like safety or even morality come in. Probably many of you have heard this kind of thought experiment about, you're in the self-driving car and it has a choice to make a split-second decision about whether to take a right turn into a brick wall and kill you or plow into a group of school children. And so, what should the algorithm do? It's a loaded question, obviously, but it's a thought experiment. And this, of course, isn't the first time that technology of some kind has bumped up against social norms. And, we have already seen in the kind of short period of the rise and ubiquity of machine learning that a lot of the traditional approaches are playing a very important role. So there's now lots of discussion about legal and regulatory frameworks for controlling machine learning and setting boundaries on what it can and can't do. And of course, many watchdog groups play an important role in that as well. What's more recent and kind of the subject of my talk today is people from the technical community, from the machine learning community itself, starting to take on this mantle and think about the ways in which machine learning algorithms could be designed to be private, fair, transparent, safe, moral, whatever you like. I recently gave a version of this talk to a general audience in Santa Fe, New Mexico, which is quite close to Los Alamos National Labs, where the atomic bomb was developed in World War II. And I half-jokingly said, there's an analogy here, because in the aftermath of World War II, many of the scientists who developed the atomic bomb started to play a key role in thinking about both technical and policy solutions to curtail its usage. And so a similar thing, I think, is happening now. And it's half joking, because it's a little bit like the people who brought you the poison now introducing the cure. But it is the right group of people to be thinking about these problems. And so, what I want to talk about today are kind of just give an overview and some particular samples from our own work at Penn on efforts to what you might think of as endogenize social norms in data, algorithms, and models. So instead of having external groups like legal, regulatory, and watchdog groups try to look at the behavior of machine learning algorithms and police it in some sense, have the algorithms do their own internal policing. And I think this is especially important when you just think about the scale at which machine learning is being applied. I'm not saying that legal and regulatory approaches won't play a very valuable, useful role, but you just can't keep up with this stuff by having people monitor and audit algorithms. There needs to be some endogenization of these concerns. And so, in fact, as many of you know, there's already now in its 4th year, very nice conference on this topic, the somewhat unfortunately named FATML, for Fairness, Accountability, and Transparency in Machine Learning, which is being held in a couple of weeks, co-located with KDD. And there's a description here of what the purpose of this conference is, but I'll just highlight the key purpose here, which is that the goal is to address these issues with computationally rigorous methods, which I think is something that everybody in this audience can appreciate. So it's not just about thinking about legal and regulatory solutions. It's about getting those solutions inside of the algorithms themselves. So let me talk about one case study in the endogenization of a social norm into machine learning that I think is relatively mature and kind of a nice case study, which is privacy-preserving machine learning. So in privacy-preserving machine learning, just to be clear here, the concern isn't like keeping the data locked down. So imagine that you're a medical researcher and you have a database of medical records of individual citizens or patients. And so for each patient, you've had some observations about what symptoms they have or have not rendered, and what test results there might be. And then maybe you have some diagnosis as to whether they have a particular disease or not, and you'd like to, let's say, run linear regression on that data and actually publish the coefficients of the resulting model. So the concern here is not, let's keep the database of patient records locked down. That is an important thing, but it's more in the domain of security. Here the concern is, does my publishing the coefficients of the linear regression model that I built from this database possibly compromise the privacy of specific individual medical records that went into the creation of that model? Okay, so that's the concern. And when I say that, I think that and then this, when I say I'm going to summarize this, it's really literally these 2 bullets. But the thing that's nice about this story, if you wade through the now large literature on it, is that first of all, there seems like there's a single strong definition, namely differential privacy, which is kind of the right definition. By the right definition, I think that most people in this audience, if you went and looked at the definition of differential privacy, you would look at it and kind of nod your head and say, wow, that's asking a lot. And if you could meet that privacy guarantee, that would be a very satisfying thing. And then, of course, the main thing you're worried about is it's so strong that it won't be very useful, that we won't be able to design learning algorithms that on the one hand meet the privacy guarantee and also are useful in practice in the sense of, let's say, having small out-of-sample error in the case of linear regression. And so, the good news here is that, in fact, you can meet this very strong definition with pretty much every machine learning algorithm that you're familiar with, not just the theoretical ones, but also the ones that are used in practice, so backpropagation and, top-down decision tree learning algorithms and boosting all have modifications that are differentially private and still enjoy, accuracy guarantees and performance in practice. So, this is hopeful news, right? This is a case where you've taken some social norm, in this case privacy, you've given a very strong, satisfying definition, and researchers have gone and systematically shown that this strong definition of privacy can be satisfied by useful machine learning algorithms. We're not seeing it in widespread practice yet, but I think it's a matter of time, especially as more and more pressure comes on the large and small companies that use machine learning at scale to be able to say something about their privacy practices. So what I want to talk about today is the same kind of agenda, but where the social norm under consideration is not privacy, but is fairness, okay? And unfortunately, we already know that things are going to be messier here. Okay, so in particular, there's not going to be one right definition of fairness, and there's going to be tensions between those definitions. So just in the last year, there have been a couple of very nice papers that to this audience I can essentially describe as like arrows and possibility theorems for fairness, right? These papers basically say, look, here are 3 properties that we can all agree any definition of fairness should meet, and you look at them and you nod your head and say, yes, yes, of course, this is, you know, kind of a minimal set of conditions we would want, and then, you know, the punchline is, of course, theorem, you can only have 2 out of 3 of these. In any case that's sort of non-trivial in some technical sense. So unlike differential privacy, I think we already know that fairness is going to be messier. There's not going to be a single right definition. We're going to have to entertain multiple competing definitions. But that's still not a reason to not go down this road of trying to design algorithms and models that are fair in one or more technical senses. Now, you know, machine learning, if you think about it, it's not just an algorithm, it's a pipeline, right? And so it's important to ask where might unfairness occur in that pipeline? And of course, the answer is it could be almost anywhere. But let me break down that pipeline a little bit because I want to use it to kind of frame the technical results I'm going to talk about today. So first of all, you know, the first part of this pipeline is data, right? So machine learning algorithms take as input sample data from some population or historical source typically. And that data itself just might be biased. So if you're trying to do predictive policing and sort of trying to say like, well, where should I put more police in order to you know, prevent more crime, you know, of course, the data that you have about arrests historically is a function of where you chose to put police in the first place. And if you chose to put police in certain neighborhoods and not in other neighborhoods, you're of course going to see more arrests on average in the places that you chose to put the police, okay? And so the data itself might be biased, okay? And so one approach, which has received some attention historically, is to think about trying to correct the data in the first place, somehow take the raw data and massage it in some way that sort of, you know, reduces the bias in some quantitative sense in that data. Now, of course, doing that is still not a guarantee that an algorithm will subsequently take your, you know, fair data set and introduce other kinds, new kinds of unfairness in it. At the other end of this pipeline, right, of course, there's the output of machine learning, which is typically a predictive model of some kind, like a linear regression model or a classifier or what have you. And I think most of the literature on fairness historically, which by the way doesn't just kind of date to the recent machine learning community, but goes back to statistics for quite a while. There are people in statistics who've thought about this quite carefully for many decades. I think it's thinking about fairness at the output of a learning algorithm that's received the most attention, and in particular, kind of notions of group fairness for predictive models like a classifier. So in particular, one of the classic notions of fairness is kind of having, if you have, you know, different subpopulations like different racial groups, and you have a model that's, let's say, giving predictively, you know, using demographic properties of the individuals in those populations to give loans, you'd like to sort of say that things like the false positive and false negative rates are roughly equal across different populations. So in other words, it's okay to deny a creditworthy person from group A a loan as long as you deny creditworthy people in group B loans at the same rate, okay? And so this, you know, this of course is cold comfort to you if you're somebody in group B who was denied a loan and were creditworthy, but at least it's fair in the sense that even though you're making mistakes in prediction, you're making the same types of mistakes at roughly the same rates across different populations, okay? And so a lot of work is about how do you design models that meet a fairness condition? And there's been very nice work from people at Google and elsewhere recently on kind of post-processing approaches to this problem. In other words, take a learning algorithm as a black box. It produces some classifier or regression model. How can I take that model and maybe some sample data and adjust the behavior of that model at the output to increase its fairness, for example? But of course, in the middle of these two things at the either end of the pipeline, there's the thing that's in the middle, which is the algorithm itself, okay? In other words, the process of going from the raw data to a model. Or you might not actually be producing a model at all. You might be more in a mode where you're making sequential decisions, and you're never kind of committing to a model, right? So, if you think about it, in the scientific literature on machine learning, it's very much dominated by this kind of train-test view of the world. You have training data, perhaps from historical data, that you're going to build a model from that, and then you're going to deploy that model in the real world and kind of leave it forever. And of course, this is a fiction, right? If you think about companies like Google or Facebook, they use machine learning, they do train, but they never sort of say like, okay, now that we've trained, the model is frozen. Every new piece of data is in an endless loop that's retraining the model, okay? And so there's this lack of a clear train-test division in many real-world settings. And so it's, I think this is particularly demands thinking about algorithms that are fair at each step. Because when there's no distinction between train or test, these things are both going on forever on every new piece of data, you don't want to kind of forgive your learning algorithm some training prefix in which it's allowed to be unfair, because that training prefix is forever, right? The training process is ongoing. And so I had the word algorithms kind of emphasized in my title because it's this kind of fairness that I want to, talk about today. Sort of not just designing algorithms that output a model that is fair, but every step along the way, each decision the algorithm is making in a sequential fashion has some fairness guarantee of one kind or another. Now, when I talk about algorithms being fair, just, one of the things that's very interesting about working in this area is that you really meet a lot of different people. You don't just meet computer scientists, you meet people from regulatory agencies and from legal groups and watchdog groups and companies that are all kind of interested in fairness. And I actually was back in the fall at a kind of, AI and foreign policy workshop sponsored by the State Department in Washington, D.C. And I thought, what in the world are we going to talk about? And what they really wanted was just to get a bunch of people who were from the machine learning AI community and kind of pick their brains and understand, understand the technical details a little bit more. And at this meeting, it dawned on me when people not from the machine learning community were talking about, the opaqueness of machine learning algorithms and how these incredibly complicated algorithms are now controlling our lives. I felt obliged to go to Wikipedia and grab this little snippet, which basically gives the pseudocode for, stochastic gradient descent, also known as backpropagation in neural networks. And my point to them was like, look, this is the actual code, right? This is the full code for, deep learning, right? There's a lot of other stuff around it. There's a lot of networking. There's a lot of, distributed computing. But the core algorithms in machine learning are like, nothing is more transparent, right? You have an objective function. That objective function is almost always some notion of predictive error and maybe a regularizer to control for overfitting. And the loop is really what I'm showing you here. For each point in the training sample, update your model, take a little derivative and reduce your error on that data point and repeat forever. And I kind of joked to them that, some of the comments they make about the algorithms being so complex, it's as if they think that what's under the hood in machine learning is a piece of code that would be on the complexity of something like Grand Theft Auto, right? Tens of or hundreds of thousands of lines of code. And so, I'm not trying to diminish the importance of concerns about the opaqueness of machine learning, but it's just important to sort of say where it is. It's not in the actual code itself. It's somehow in the interaction of that very simple piece of code with complicated data and, of course, the creation of some very complicated nonlinear model whose internal workings and features we don't understand. So I think it's less at the algorithmic level than it is at the inputs and the outputs. Okay, so given all of this, I think the sort of sober scientific methodology one should pursue is the following sequence of steps. We need to do research in which we pick a particular learning framework or problem. We commit to some technical definition of fairness with the understanding that there is going to be more than one of them that are reasonable and that they are going to potentially be in tension with each other. And then, of course, for that particular pair of choices, a learning problem and a definition of fairness, we have to explore the consequences. We have to ask, can we design algorithms for that problem that are fair by that definition of fairness? And are there also barriers to that? Are there impossibility results or lower bounds, and do they match what we have in the upper bound? So kind of exactly the type of thing that this community of people is very familiar and comfortable doing. But in this case, on the topic of learning algorithms and different notions of fairness. And so the goal, of course, is to understand what are the inherent costs of fairness, right? There's going to be some, it can only make machine learning harder for me to ask to do what we do in machine learning and also have it be fair in some sense. So it can only be a harder problem, and what we'd like to do is to understand how much harder that problem might be. And then, of course, we need to repeat this loop because of the fact that we already know there's not going to be a single monolithic correct notion of fairness. Okay. Okay, so what I want to just tell you about today is a particular definition of fairness that we've been exploring in our group at Penn that we've come over time to call weakly meritocratic fairness. And just to be clear here, especially in light of what I've said so far, I'm not really here to sell you on this particular definition of fairness. I'm here to sort of show you a case study in committing to a particular definition which seems to have some nice properties and some obvious weaknesses, but to kind of systematically try to explore the consequences of that definition in a number of different learning problems, okay? So to talk about this notion of fairness, I want to begin by positing that there's some ground truths. Imagine that there's a population of individuals, and imagine that for the most part, these individuals are represented by feature vectors, right? So to give a concrete example, if we're thinking about a population of applicants for loans or mortgages, these people will have filled out applications. We might know some information about them from that application. We might know their gender, we might know their race, we might know their employment history, and we might know their zip code, we might know their credit score, we might know their educational background. So I'm going to kind of summarize that as some abstract vector of observations that we have about that individual, a feature vector, if you will. And so my starting point, which by itself is already controversial, especially when you talk to people from legal, regulatory, or philosophical backgrounds, many of the things that are taken for granted in the machine learning community are already objectionable to people from those communities for good reasons. But I'm going to imagine that there's some unknown mapping, if you like, from the observed properties or features of individuals to something that we really like to predict or make decisions on, okay? So for instance, in the case of mortgages, this might be the creditworthiness of an individual. We'd kind of like to come up with some estimate, given your loan application, of how likely you are to repay the loan, okay? If it's employment, it might be your qualifications for the job or your probability of success in college admissions. It might be, the probability that you do well by some measure in college. And so we're going to imagine that there's some mapping, some function which takes the observed properties of an individual and gives us that magic number on which we'd like to base our decisions, okay? And the key thing that I'm generally going to be assuming here is that functional mapping is simple in some sense, in the machine learning sense. It permits some parametric model, but it's unknown to us, okay? So it might be a linear model, but we don't know what the coefficients of the linear model are at the beginning, okay? And so I'm going to imagine that the observed scores can be noisy, right? So that, like, let's say in the case of loan applications, I assess the creditworthiness of a particular individual, and maybe that's a real number between 0 and 1, which is the probability that I think they're going to repay the loan. But of course, at the end of the day, I just find out whether they repay the loan or not. I don't learn the true probability. So we're going to allow for modeling noise of that kind. As an aside, I won't say a lot about it. I think true unrealizability in the sense of machine learning, meaning that you have no assumptions, you're not allowed to make any assumptions whatsoever on this mapping, is not just a technical but a conceptual challenge for fairness, and that needs deeper thought than we've had time to give it so far. But so what am I going to mean by fairness? So, like for those of you that are familiar with machine learning or learning theory, all I've done right now is introduce what we would call a target function there, right? There's some unknown mapping from observed vectors to outcomes, and we'd like to data build an approximation to that model. So what is fairness going to mean? Fairness is going to mean that, if I call this mapping a quality score, that if the quality of individual A is at least as high as the quality of individual B, then we can't favor B over A, okay? More precisely, what I'm going to mean is that in a probabilistic sense. So let's say we're talking about classification. We're talking about, which individuals to choose to give loans to. So if A is at least as creditworthy of B, the notion of fairness we're going to adopt is that you have to choose A or give A a loan with at least the probability that you're going to give B a loan, where this probability is strictly over the randomization of the algorithm, okay? And by the way, again, if you talk to people in law or philosophy, as Aaron and I have done at Penn, and you ask them like, well, how does the law feel about about randomness in decision making? There's a lot to discuss there. So this is again one of these things that in the computer science community we take randomness in algorithms as a given and a natural and useful thing. To people in those communities, talking about randomization in decisions, for instance, about loans or employment is a controversial thing already. So it's another one of these examples where, we think, well, of course, the right answer is a randomized algorithm. To them, that's not an easy step to take. Okay, so this is the type of definition I have in mind, right? There's this mapping from individuals to some true quality score we'd like to predict, and if one individual has at least the quality of another, you've got to choose them with at least the same probability, okay? Let me immediately make two technical points about this definition that you may or may not like, but it's a fact about this definition. So I'm basically saying if A is at least as good as B, then you have to choose A with at least the probability that you choose B. I'm not saying if the first inequality is strict, that the second inequality has to be strict also. So I'm not saying that if A is strictly better than B, that you have to choose A with strictly higher probability than B, okay? So this is important, right? Because in particular, it means that a lottery is going to be fair, right? So if I have two individuals in front of me and one of them is just way, way better than the other one, it's going to be fair to flip a coin to choose between the two. And this might seem like a technical point, but let me point out a particular kind of discrimination that it does allow, even though the algorithms I'm going to describe to you don't engage in this kind of discrimination. It would be the kind of discrimination where, let's say African American and white applicants are arriving sequentially over time. And this definition would allow you, for instance, to any time that a white applicant was better than a black applicant, to deterministically select the white applicant, and anytime the black applicant was strictly better than the white applicant, to flip a coin, okay? So that's being allowed in this definition, and so that's not without controversy, and it's worth thinking about. And so this is one of the reasons why we call it weakly meritocratic, right? It's basically saying if somebody's as good as somebody else, you have to choose them with at least the same probability. It's not forcing you to kind of choose better people. Okay? It also doesn't bind across time, right? So I'm also not, if you imagine that you're showing up for a loan on a particular day and I'm deciding which of you gets loans today, I have to obey this definition at each step. but I'm not promising you that you won't be chosen with a lower probability than somebody worse than you that arrived 10 days from now, okay? And this, I think, if you think about trying to fix this, I think it's quite hard technically, at least in the bare bones model that I'm describing here. But this is an example of sort of some of the, the choices you end up making when picking definitions of fairness and why there's sort of tension between different definitions, okay? Okay, but let's fix this definition for a moment, and let me just make two observations. One is that optimal decisions are fair. So if we think of ourselves as the loan giver and we'd like to give loans only to the people that are creditworthy, that's going to be fair by this definition. So that's kind of a technical thing that's nice from the perspective of machine learning. It means that ultimately making perfect decisions from the decision maker's point of view, in the sense of, let's say, giving loans to more qualified applicant, that's going to be fair by this definition, okay? But as I mentioned, it's also fair to entirely randomize between the candidates in front of you at each round, right? So if there's 5 people in front of me, just choosing, if I'm gonna choose, let's say, one of them, picking uniformly at random is also fair, okay? And so this sets up a nice technical problem, which is, because we don't know this mapping from observables to quality, at the beginning we can't be optimal, right? That's the entire point of machine learning, is to sort of take sample data or decisions over time and move from not knowing anything to knowing enough that you're making optimal or near optimal decisions. But you can't make optimal decisions at the beginning, otherwise you wouldn't need machine learning. But so this sets up a nice technical question, which is there's something you can do at the very beginning which is fair, which is a lottery. And we also know that asymptotically, if you learn the true quality mapping, you can be fair and optimal. And the question is, is there a fair path between these two, okay? So let me describe one setting in which you can indeed get a fair path from knowing nothing to being asymptotically optimal, and in fact get good rates of convergence to optimal decision making as well. So I'll describe that in a second. But in addition to the kind of drawbacks I've pointed out so far, there are many important issues that this definition doesn't address. So for instance, it doesn't address kind of the question of incentives, which is, what if we're not designing the algorithm, but we're trying to convince some other party to be fair by this definition? How would we get them to care enough or incentivize them to be fair by this definition? I'm not yet addressing feedback between decisions and quality, sort of affirmative action styles of fairness. I am going to talk about these 2 bullet points and ways that you can address them. But then there's certain other things that come up in discussions of fairness that are sort of almost feel like they're outside of the boundaries of mathematical modeling. So a lot of times when you discuss fairness with people from non-technical communities, part of the goal of fairness is to redress past wrongs. It's not that you're, trying to be fair to people now. It's that some injustice was committed against a community of people historically, and you're just kind of trying to repay that. And so it's important to realize in this arena that, there's all these different notions of fairness, and some of them, when you sort of try to write down a version of it, have technical problems, and some of them it seems like hard to even write down. Okay. But let me talk about fairness in sequential decision-making first. So what I mean by sequential decision-making here, I'm really thinking about multi-arm bandit problems, in particular contextual bandit problems. So let me kind of take the definition I gave on the last slide and tell you how it plays out in the case of contextual bandit problems, okay? So just to summarize and recap, I think most people in this room are probably familiar with these models in one form or another, but let's imagine at each round, some number of individuals arrives in front of us. Let's say they're loan applicants, and for each one of them, we have a feature vector describing the properties of the applicant. And these individuals might be from different demographic subpopulations. They might be from different racial groups, different gender groups, whatever you like, okay? And at each round, we can choose some number of them to accept, so to speak, give loans to. But we want to do so fairly at every round, and we don't just want to be fair at sort of the group level in the kind of traditional equal, false positive, false negative rate. We actually want to sort of give some promise that we've treated the specific individuals who've arrived in front of us at each round in a fair way relative to the other individuals who arrived at that same round with that person, okay? And so again, once again, I'm imagining that there's some unknown but parametric function mapping the observed feature vectors of the individuals to their true quality. And this is a bandit problem because we're only going to get feedback about the outcome from the individuals that we accept, right? We only find out about whether people, we only find out whether people repaid the loan to people that we actually gave the loan to. We don't find out what would have happened to people we chose not to give a loan to, okay? Okay, so there's a classical algorithm for this problem. In the case, for instance, of a linear model where the mapping from observed features to a quality score is just a linear regression model. And this is the so-called UCB, or upper confidence bound algorithm, which is kind of an instantiation of this general principle in exploration-exploitation problems of optimism under uncertainty. And so let me just describe to you in kind of a picture how this algorithm operates. So let's imagine at some particular round, this looks quite hard to see, but let's go for it anyway. So let's imagine at some particular round, these 7 individuals have shown up represented by vectors x1, x2, x3, x4, et cetera. And they each have some true unknown quality score, which is kind of a weight vector beta times that x vector. But we don't know what the betas are, okay? But what we can do from sort of standard statistical concentration inequality results is maintain confidence intervals around each individual's true quality, right? So maybe the true quality of individual 1 is beta x1. We don't know that. What we do know is that it falls somewhere between a lower bound L1 and an upper bound U1. And we have that for all of the individuals arriving at each round. And so let's suppose, just for the sake of simplicity, that at each round we want to choose one individual. Okay, this would be the classic bandit problem where you have to pick one arm to play at each round. By the way, it's important, as we learn from critical reviews of some of our papers, to sort of not just, especially if you're thinking about mortgages, one very good criticism we got, and again, this is an example of like, well, let's think about this simple model, it'll be easy to generalize, and the reviewer's like, no, it's like this generalization is really important, is to sort of not stay in this model where you can only pull one bandit at each time step or only give one loan, because then you're kind of setting races off against each other, right? If you really say like, look, I don't care how, even if they're all credit worthy, I'm only gonna give a loan to one individual, then you're sort of introducing a needless competition between individuals or the groups that they're from. You should really be in a model where you can, pull any arm or give any loan that's profitable. But, and you can generalize everything I'm going to say to that setting as well, but let's for now stick with the case where we're just going to pick one individual. So the UCB algorithm would kind of look at these confidence intervals and ignore the confidence intervals themselves, just look at the upper confidence bound, which is why it's called UCB, and just greedily pick the upper confidence bound that's the highest. Notice that this is not the greedy algorithm that is choosing the thing that empirically has been the best so far, right? It's not picking the group or representative that's been empirically the best so far. It's picking the thing that has the highest upper confidence bound in a deterministic way, okay? And the reason this algorithm is a good algorithm is that the exploration step becomes implicit, right? Because the more, if something keeps looking good and you keep trying it, then your confidence interval on it narrows. And so the sort of bonus that you're giving it for your uncertainty is lower. And then you'll start naturally exploring other things whose confidence intervals are wider. And in this sense, kind of narrow all the confidence intervals enough to know that you're making optimal or near optimal decisions. Okay. So, looking at this picture, the UCB algorithm would choose candidate 1 because they have the highest upper confidence bound. This will badly violate fairness, right? Because it could easily be that given these confidence bounds that individual 2 actually really has the higher value. And then we will have treated individual, if we deterministically choose individual 1, we will have, by the definition of fairness I gave on the last slide, be unfair to individual 2. So if you use this definition and you just run the standard, bandit classical UCB algorithm, you will badly violate fairness, many, many times in the learning process. Asymptotically, it will be fair because asymptotically, UCB is optimal. Okay, but on the path to asymptotic optimality, it might make many, many unfair. It might be making sort of a linear fraction of unfair steps. Okay, so. So you can fix this, and sort of the fix is kind of obvious if you think about it. What's kind of nice about this is that the algorithm is sort of forced on you. I claim that really there's only one fair algorithm at a high level if you think about it, with variations on it, which is, look, given these two confidence intervals, they overlap. So I'm uncertain about which is better, individual 1 or individual 2. So I have to choose them with equal probability. And individual 3 overlaps with individual 2. So to treat 2 and 3 fairly relatively to 2, since I'm choosing 2 with some probability, I have to choose 3 with the same probability. Okay? Notice how, if you can see this picture, I absolutely know for certain that individual 3 is worse than individual 1, because their confidence intervals don't interlap. But you have this transitivity property that forces you to choose something that you know that's suboptimal, because otherwise you're going to be unfair with 2 relative to 3. So you have to do what you would call confidence interval chaining, right? You can't just look at these intervals and take the best one. You have to take the first one, take anything that overlaps with it, and chain them together. And at some point there will be a break, there might be a break in the chain. And so in this particular example, we would choose the first 4 individuals with equal probability, and we would not choose the last 3 individuals at all. Or we would have the uniform distribution over the top 4 individuals. Okay, and this is just a visualization of this algorithm in simulation, running over many rounds in a case in which there's sort of 5 different groups from which individuals are being drawn at each round. And you can see that what's happening over time, and I'm showing you the actual confidence intervals. Because it's a contextual problem, the representative from the blue group is different each day, and on some days the representative from the blue group is better, and on some days it's worse. And so which is the best candidate of the 5 from the 5 groups on each day is changing over time. It's actually annotated here, but you can see sometimes blue is higher, sometimes red is higher. And so you're needing to, which individual is the best is changing, but the important thing is that this, what the proof of this algorithm's correctness and fairness looks like is you're basically arguing that you're guaranteeing fairness because you're doing this chaining, but then you still need to analyze sort of the rate at which these confidence intervals shrink when you're playing uniformly at random over the upper interval chain, okay? And that's kind of the, how the proof goes. And so what's the upshot of this? So in the case that I've been discussing, where the mapping from observations to quality scores is linear, you get an algorithm that's provably fair at every step. Okay, so it'll meet the definition of fairness I described at every single round, regardless of which individuals show up at that round. And you get like a cumulative regret bound that looks like the square root of k cubed times t, where k is the sort of number of different subgroups that you're choosing between at each round, and t is the number of time steps. Okay, so this is good. We have a fair algorithm, and it has sublinear regret. And so asymptotically, it's approaching optimal decision making at a rate that looks like, this divided by capital T, so square root of k cubed divided by t, okay? We also know that this dependence is tight, so you can prove that any fair algorithm will essentially has to have this same dependence on k, okay? Whereas in the case of UCB, you get a bound that looks like this, except the k cubed is replaced by k. And so another way of thinking about this is that the number of rounds you need to run UCB before you're getting non-trivial regret is about order k, whereas this algorithm, the fair algorithm, requires order k cubed, and we know that that's tight. So this is nice and an example of sort of the agenda that I'm advocating here. We picked a learning problem, contextual bandits. We picked a fairness definition, which is the one that I described. We sort of went through the consequences, gave a fair algorithm. We know that it is asymptotically optimal, but at a provably slower rate than ignoring fairness. Okay, and so this is quantifying really the cost of fairness. There's actually a more general equivalence between contextual bandit problems, linear or otherwise, and something that's known in the machine learning theory community as quick learning, for knows what it knows learning. And through that connection, you can show that there are other cases where this gap between the regret that you suffer ignoring fairness and the regret that you suffer demanding fairness is actually exponential rather than the polynomial that we're seeing here, okay? So this is a good case, but there are also bad cases, right? And those bad cases can be simple. In the particular case that I'm describing here, it's where instead of that being a linear model mapping features to quality scores, there's something more like a conjunctive model, okay? Okay, so let me go on to discuss kind of variations of this definition for other learning problems. So in particular, and this is maybe the slide where we come closest to EC-like topics versus pure machine learning topics. What I've described so far kind of assumes that we have the luxury of designing and deploying the algorithm of our choice to meet a particular definition of fairness, okay? But especially since, in this arena, one talks a lot with regulators and watchdog groups and the like, there's also interest in the question, well, what if you don't control the algorithm but have some oversight of the algorithm, right? And so in particular, if you think about trying to convince a company like Google to design learning algorithms that are more fair, either you can harangue them and try to get them to do it of their own volition, or you might think about incentivizing them or regulating them in some way, okay? So what if we don't control the algorithm directly, but we can shape the decisions that an algorithm makes via payments, for example? And so you might imagine that the principle that's sort of making these payments exogenously is a regulator, or it might be like a technology platform. And so in the latter case, imagine sort of things like Prosper, which is a peer-to-peer lending site, or perhaps more familiarly Airbnb, which is a peer-to-peer short-term rental site, okay? So you might imagine that in that setting, the agents, in the case of Prosper lenders and in the case of Airbnb landlords, they might choose to be myopic and therefore discriminatory in some sense. So, an Airbnb landlord might just be mainly concerned at renting to people that won't trash their apartment when they're away, for example. And it could be that, there's some correlation between that and systematic discrimination against one particular type of individual or group of individuals. There's actually an interesting recent paper that did an empirical study of discriminatory behavior and kind of racist or apparently racist renting practices on Airbnb. And one of the interesting things that they suggested there is that there might be an element of myopicness to the behavior of apparently discriminatory landlords on Airbnb, in the sense that in their data they showed that people who had never rented to a particular racial group were more likely to be discriminatory in their decisions against that group than people that had rented to that group before and had discovered that actually, it went fine, okay? So let's imagine a setting in which there's an algorithm or more precisely a population or collective of agents like Airbnb landlords that are rational, but they're myopic, right? So they're going to make kind of decisions that aren't thinking about the longer term consequences, but are sort of optimal or greedy in some immediate sense. So think, instead of something like UCB, think about the actual greedy algorithm that just picks the group that has the highest empirical mean so far in terms of payoff. So the agent is myopic in that sense, but it's also rational in that if we sort of say like, look, given that you have these two choices in front of you and you're going to make choice A because historically that's given you higher payoff, I'm going to provide you a little bonus if you'll play group B, and if the payoff for group B plus the bonus we offer is greater than the payoff for the myopically estimated payoff for group A, then they'll go ahead and take B, make decision B and take our payment, okay? And so when you're talking about an exogenous party providing incentives for an algorithm, it's important to sort of talk about what the informational model is, sort of what does the regulator or platform know about the internal state and data that the agent has gathered so far. And so we kind of consider two settings. One is the full information model, where in particular the principal will not just see the decisions that the agent has made, but the actual outcomes. So it's like if you're a loan or mortgage regulator, you'd get to see not just which individuals the agent had decided to give loans to, but you would actually see the outcome of those loans, right? And so that might be a very strong assumption depending on the problem in the industry, right? It could be that that's proprietary data of the agent that the principal or regulator wouldn't be allowed to see. And so you also might want to consider weaker models like the partial information model, where the principal sees only the decisions made by the algorithm or the agent, but not the outcomes of those decisions, okay? And there's other, information models you could consider as well. I won't go through this, but I ask you to go see Stephen Wu's talk on this topic in the Thursday, roughly 11 a.m. session. I think he's towards the end of that session. But we basically kind of, again, revisit bandit problems, both the classic bandit, multi-arm bandit problem and the contextual bandit problem in each of these informational models, and find some sort of fairly stark, sharp trade-offs. So in particular, in the full information model, whether you're in the classical or the contextual case, you can do well in the sense that you can kind of incentivize fair behavior that's asymptotically optimal for the agent at a cost in terms of the cumulative subsidies you have to give to the agent in order to incentivize fairness that's sublinear, okay? So that's good. Whereas in the partial information model, things get much, much harder, sort of impossible in the case of linear contextual and possible under some particular conditions in the classical case, okay? And so I'll leave it. I'll leave the punchlines and technical details on this to Stephen's talk. Okay, so another kind of lack in the definition and the examples of that definition I've given so far is that we're not accounting for influencing the future. And in fairness circles, this kind of topic comes up all the time in different forms. But at a high level, the problem here is that, for instance, bandit settings don't model the influence that our own actions might have on some underlying notion of the state of the world and future payoffs. So to put that more in English, an example would be, perhaps investing in a disadvantaged community that is not particularly creditworthy or is less creditworthy right now. Because I'm investing in that community, it improves that community's economic fortunes in a way that over time actually raises the collective creditworthiness of that group, okay? Or perhaps by admitting some disadvantaged group into elite universities over time, even though they're less qualified than other applicants at the moment that I'm admitting them, improves the prospects of that community till eventually actually the applicants from that community do become quite qualified, okay? So this is the type of fairness consideration that I want to talk about now. And it's often an implicit rationale, not the only one, behind kind of affirmative action notions of fairness, which I'm sure many of you have heard in one form or another. And at a high level, the fundamental question here is sort of what is the appropriate time scale for fairness, right? Sort of, are we trying to be fair on sort of a short time scale, i.e., to the individuals literally who've shown up in front of us today? Or are we also, or perhaps instead, trying to be fair in some longer term sense that accounts for the fact that our very decisions can change the relative prospects or quality, if you like, of different groups and individuals over time, okay? Okay, so, if you're from the machine learning community and you sort of, take my first bullet point there and say like, well, we want to think about learning settings in which the decision maker's actions have influence on the future, the natural framework of that, of course, is reinforcement learning and Markov decision processes. And so one can take the same fairness definition I've been using so far and apply it in kind of a straightforward definitional way to reinforcement learning, in which, and again, if you're not familiar with reinforcement learning, there's this fundamental notion called Q values, which is, what is the quality given the current state of the world and a particular choice or action that I'm going to take, what is sort of the longer term payoff that I get from that, accounting for the influence that my action has on the future state of the world and therefore on my future payoffs as well. So that's what Q values capture. And so I could give a definition that looks like, well, I'm now going to ask that if in a particular state S, the Q value of action A is at least the Q value of action B, then from that state, the probability that I choose A has to be at least the probability that I choose B. So it's the same definition, but now accounting for this kind of future influence. And so it's easy to adapt the definition to the machinery of reinforcement learning. And now you immediately find that you kind of come up against very, very strong barriers to fairness. In particular, you can sort of show that if you take that definition of fairness and ask for fair reinforcement learning in general Markov decision processes, you immediately get kind of exponential lower bounds. And the example is actually quite simple. It comes from the fact that, under this definition of fairness, if there's some state, so this is a sort of simple Markov decision process where there's two actions going right or going left, which returns me to the initial state. And if all of these states kind of are giving the same payoff, regardless of what action I take, and then there's one state out at the far end where the payoff might be much higher than states or much lower, because of the discounting in reinforcement learning, the Q values of kind of going right or going left at the initial state are going to be slightly different depending on the payoff of the state way out here, but that difference will be exponentially small because of the discounting. And so a fair algorithm is sort of forced to take a random walk, and that random walk will only ever visit this state after an exponentially large number of steps. An unfair algorithm can just be aggressive in its exploration. It can just say, look, I want to deliberately get to states that I haven't visited before, so I learn about the rewards there. And it would just kind of march way off to the right here very quickly. And so this is what sort of standard algorithms for non-fair reinforcement learning do, and they can learn a general Markov decision process in polynomial time, ignoring fairness by being aggressive in their exploration. Under this definition of fair, you can't do that, and you get this exponential separation. But if you relax the definition of fairness a little bit, or maybe a lot, you can actually recover kind of fair versions of reinforcement learning, kind of a fair E cubed or R max if you're familiar with that family of algorithms. And the approximate notion of fairness is sort of, again, technical but conceptually worth thinking about and what its drawbacks are. So in particular, I'm now going to ask that if the Q value of A is bigger than the Q value of B by at least some gap alpha, then I have to choose A with the same, at least the probability that I choose B, okay? So if you use that relaxed definition where I only have to obey this fairness condition if there's a bit of a gap between two actions, then you can get a polynomial, provably fair and polynomial time algorithm with a Pauli dependence on this inverse alpha. But just to be clear here, this permits treating nearly equal Q values in an arbitrary way, right? So if from a particular state of the world, two individuals are roughly equally creditworthy, i.e. their creditworthiness is within alpha of each other, then I can treat those two individuals arbitrarily any way I want. I could sort of, deterministically pick one of them over the other one, even though they're very, very close. And again, and so this is sort of, again, kind of a weak or one-sided definition of fairness, right? If you're way better than somebody, I'm giving you some guarantee that you'll be chosen with at least their probability. But if two of you show up in front of me that are equal, I could just systematically choose the white candidate always, okay? And again, that's not something I think we would be happy with, but that's the consequence of this definition. And if you try to drop that, you kind of come up against this exponential barrier. Okay? And again, even just to be clear here, even though I'm now talking about time scales of fairness and accounting for the influence that our actions have on the evolution of a group, I'm still not, addressing this. I'm addressing influencing the future, but I'm not addressing fixing the past, i.e. redressing past wrongs against a particular group. Okay, so the last little vignette I want to kind of close with and hopefully leave a little time for questions is, one assumption that, again, is quite common, but you start to wade out of computer science circles to people who've thought about fairness from other angles, and you quickly realize that a lot of your, things we take for granted are controversial to other groups. I've been assuming so far in all of these different models and problems that individuals can kind of be put on a common scale that allows numerical computation numerical comparison between them. So this notion of quality or creditworthiness. And it really could be that that's not possible. And I mean this in a strong sense. So, a weak version of this that can be addressed in all of the frameworks I've discussed so far is where, let's say we're thinking about college admissions and there's two demographic groups, and one of them has systematically raised SAT scores because it's a wealthy subpopulation in which families can afford and do pay for SAT preparation classes, okay? So in that group, we're going to expect the SAT scores to be systematically elevated relative to the group that can't afford that. But it doesn't mean that that group is any more qualified for college or likely to be successful in college. They just paid for SAT preparations classes, so they do better, okay? So that I can deal with in the framework I've discussed so far by sort of having allowing different models or functions mapping observables to quality scores for one group versus another, right? So for maybe the wealthy subgroup, I should put less weight on their SAT scores in their college application because relative to the other group, right? So I'm going to kind of discount that. So this kind of numerical adjustment to put things on the same scale is something that can be incorporated in the models I've discussed so far. But there are really other situations where you just have different groups with different metrics on them, and there's just no way you can compare them numerically, okay? So what I mean by this is things like musicians versus athletes, right? So, let's imagine, for instance, that all musicians, and this is, of course, already a bit of a cartoon, but let's imagine there's some quality score for musicians, which, maybe measures the difficulty and skill with which they play different pieces, and maybe for athletes, let's say track athletes, it's their race times, okay? So how do you compare these two, right? This isn't like the SAT score example where I can make some numerical adjustment to normalize the values between two groups. These are just incomparable values. Maybe to pick a topic that's closer to home, what about subfields of computer science in faculty hiring, for instance, right? So, you've interviewed some theory candidates, you've interviewed some ML candidates, you've interviewed some system candidates, and each one of these individuals comes from a completely different subcommunity with different publishing standards, different rates of publication that are common, et cetera, and it's just not easy to kind of put them on the same numerical scale, yet when you do faculty hiring, you're forced to make choices between these different individuals, okay? So, in the work that I'm describing, the approach that we take is we imagine that what we're really interested in is the true, what you really want to do for each individual is rank them within their own group with respect to the underlying distribution, okay? So for example, let's say you're, at a place like Penn, the track coaches are looking at incoming freshmen to decide who to give athletic scholarships to, okay? And so, you have a bunch of candidates who've run the 100-meter dash in a particular time from who are women and some who are men, and of course those times are different. But what you really care about is, this particular race time for an individual, for a female candidate, how does that compare not just to the other 100-meter times of the people who applied that year, but to the sort of historical distribution all time, okay? So we imagine that there's there are these distributions from which values are being chosen from different groups. Of course, we get a bunch of examples from each subgroup at each round, and we can rank them within their group. But what we really want to do is figure out how that person sits with respect to, the background distribution in the entire population of, let's say, 100-meter times, for example. And I would argue that, the way letters of recommendation are written for faculty hiring are essentially trying to get at this, placing individuals with respect to the all-time background distribution of their subgroup when people say things in their letters like, this is the best student in algorithmic game theory in the last 5 years, right? That's an effort to sort of say not just, where they are relative to the applicants this year, but somehow put them in in the broader context. And, it's different to say this than to replace the 5 years with the last 25 years, for example, which would be a stronger statement, okay? And so, the formulation we look at is that some number of sampled candidates from each of k distributions arrives at each time step. You, of course, can rank them within their subpopulation, but you don't have direct comparability across subpopulations, and you again want to ask for some notion of meritocratic fairness with respect to the true CDF value of each individual with respect to their underlying distribution, okay? And to save a bit of time here, let me just say that you can do this. There's a very simple algorithm which you kind of assign a score based on the empirical ranks and the confidence intervals you can give around the CDF values. You then add noise to those scores, merge the scores from the different subpopulations, and then pick the top candidates. And this has provable fairness properties of both an exact and an approximate way, and you can talk about sort of the regret that you suffer compared, again, to an optimal algorithm that ignores fairness entirely, okay? Okay, so conclusions. So the particular definition or class of definitions that I talked about today, meritocratic fairness, has some nice properties. It permits provably fair and efficient learning algorithms, incorporation of incentives, consideration of influence on future actions and timescales, and adaptability to settings where you can't make direct comparisons across different subgroups. It has a lot of drawbacks too, right? I think one of the biggest ones is that not in all of the results I've described, but in many of them, including the contextual bandit results, we're really making this realizability assumption that the real model is a linear model, and it's not that if you drop that assumption, it's that there's sort of graceful degradation. It's not even clear what the right definition of fairness should be when you're forced to choose a parametric model for reasons of simplicity, and the world might be arbitrarily complicated. In many ways, it's a weak definition. It doesn't, deal with sort of strong meritocracy where if you're strictly better than me, you should really be chosen with a higher probability. And then there's some things that just seem completely out of the scope of even this type of definition at all, which are things like redressing past wrongs. In general, setting aside this particular definition of fairness, all this work is very, very early days, and we don't yet have a good understanding of fairness performance trade-offs of a more nuanced variety than I've described here, either in theory or practice. So for any given learning problem or any given definition of fairness, what we'd really like to be able to do is kind of trace out the entire Pareto frontier of the bi-criteria problem of minimizing fairness and predictive error in tandem. This is an actual empirical plot of such a curve for a particular data set, which is this criminal recidivism data set, with a particular notion of fairness for regression problems, where the predictive error is, out of sample squared error. And so we need to come to better understandings like this because, society is going to, in some sense, have to get used to looking at pictures like this and making choices, right? Sort of deciding, given the importance of your application and the harms caused by unfairness versus the harms caused by predictive inaccuracy, where you want to be on this plot, right? Do you want to have a model which, has a lot of unfair, is very fair but has high predictive error, or a model that's very unfair and has low predictive error? And of course, these kinds of decisions should be made based on pictures like this that are specific to particular data sets or domains or problems, and in which the decision about where to be on this curve depends on kind of what's at stake, right? I mean, where you might be on this curve might look very different if it's a decision about what ads you show on Google versus what criminal sentence you give somebody, okay? This perhaps is the largest picture wall outside of particle physics co-authorship lists, but I want to thank my terrific colleagues. There's a kind of a small army of us that are working on this stuff at Penn, and we've been having great fun doing it, and I'm also just providing some quick references to the works that I discussed. So thanks for listening, and I'm happy to take questions or comments.